Hello friends, welcome to Mu Lessons. Here we are again with a new topic that is about the several theorems of circuit and network. So basically we will start with this chapter. This is about the circuit theorems. Now in this video we will discuss some important fundamental theorems of the network analysis. Those are used and very much helpful in solving complicated networks and meshes. There are certain theorems like the superposition theorem, Thevenin's theorem, Norton's theorem, maximum power transfer theorem, substitution theorem, Millman's theorem and reciprocity theorem. So we will go as we will proceed in this video. So just for the basic purpose, we will start with the linearity property of these networks. The linearity is the property of an element describing a linear relationship between the cause and the effect. A linear circuit is one whose output is linearly, or you can say directly proportional to its input side. For example, if you see in this whole mesh of IS, which is the current is given as 15 ampere, and I4, I2 and I1 are respective currents in the several branches of these networks, and these branches are connected to several different types of resistors. Now if Is is equals to 15 ampere, then IO, that is the output current in the whole network, is 3 ampere, and if IA is 5 amperes, then I output becomes 1 ampere. So this shows that the linearity principle, or you can say the property of linearity, says that the input is directly proportional to output. We have also came across these types of things in case of Ohm's law, where V is directly proportional to I and so on. Now the first theorem is the superposition theorem. This superposition theorem principle states that the voltage across or the current through an element in a linear circuit is the algebraic sum of the voltage across or the currents through that the elements due to each independent source acting alone. So in this case we need to consider an independent source, and that has to act alone, and we will find the effect of that source on that particular branches or whenever it is acting alone. And at last we will consider, or we will take the effect of all these branches and all these sources together. For that we used to find the solution. This is used, that is the superposition theorem is used to find the solution to networks with two or more sources that are not in series or parallels, or the current through or the voltage across an element in a network is equal to the algebraic sum of the currents or voltage produced independently by each source. Since the effect of each source will be determined independently, the number of networks will be analyzed will equal to the number of sources. Now to follow this superposition theorem, there are several steps to apply. Like the first step is turn off all the independent sources except the one source. Find the output voltage or current that is due to the active source using the nodal or mesh analysis. Then you need to repeat the first step for each of the other independent sources. Now find the total contribution by adding algebraically all the contributions due to the independent sources. So you can see from this diagram, in this case this is the complete diagram. We have two sources, that is this is E is given denoted as a voltage source and I as a current source, and this is the network. Now we have to analyze the effect of both the sources independently. So we can assume it is to be, for the first case we assume only current source is available and the voltage source has to be short circuited. Remember, the voltage source to be short circuited and the current source to be open circuited. And the second case, when we are considering the EMF, that is the voltage source, then the current source should be open circuited. Now by applying these two processes we can get the two values. Like in this case we get V equals to V1 plus V2, and for the second case we get I1 plus I2. And finally, while solving the numericals, we will see how we are using combinedly these two processes and we will getting the net result. Now for example, you can see from this picture, this is a mesh. It has a current source having 3 ampere and a voltage source of 6 volt. Now there are two resistances, that is 8 ohm and 4 ohm connected. Now we have to use the superposition theorem. Now we have two processes, or we can split this whole network into two different halves, that is A and B. In case of A, we are considering the voltage source, so we are open circuiting the current source, and the second case we are short circuiting the voltage source and considering the current source. Now for each of them we get the values, like for this case we get V is equals to V1 plus V2, and hence V1 is equals to 2 volt given and V2 equals to 8 volt. So the net V is equals to 10 volt. So in this way we can solve some problems considering or helping, and these types of substitution theorems also help in solving large number of meshes and long networks. Now in this case there is another very important part, that is about the source transformation. This source transformation has a key role in minimizing the circuits and analyzing it in a different way or in a simpler way. So a source transformation is a process of replacing a voltage source Vs in series with a resistor R and by current source Is in parallel with a resistor R. Or you can say that Vs equals to Is into R, or this Is equals to Vs by R. Now suppose this is the part of a circuit, that is it has a voltage source Vs and it is connected to a resistor R. Now if you want to convert this part into a current source, then what you need to do is replace this Vs with a current source Is, and this Is value will be given by Vs by R, and subsequently you need to connect that resistance in parallel with this current source. Now these two parts are equivalent to each other, but only the difference is this is a voltage source and this is we have converted or we have transformed into a current source. These types of techniques are regularly used in solving this meshes, because this make the network very easy to solve. Now it can also be applied to dependent sources, like for this case it has a dependent source. You can already know how the dependent source look like. It has in the shape of a rhombus. Now Vs is a voltage source, that is a dependent voltage source, and Is we are converting into a dependent current source. Now similarly in this case also Is will be Vs by R, and hence and subsequently the same R will be in parallel to the current source. Now for example, you need to calculate the output, that is V output, V0 or V output across, or the potential across 8 ohm resistor. Now you need to analyze it, how it will be easy for you to solve. Now in this case you can see there is a current source and there is a parallel resistor 4 ohm. So we can convert that current source along with the parallel resistor to a voltage source and the same resistor in series. Now see how easy it has become. We are only having two voltage sources, a voltage source, some resistance and a simple current source. Now by solving or minimizing or taking the resultant, or you can say taking the equivalent of all these resistances, you get it as 6 ohm, 8 ohm, 3 ohm in parallel with two opposite current sources. Now in this whole circuit we are dealing with only current source and the net resistance. So easily we can find what is the voltage across this network, this branch, that is of 8 ohm, and the voltage across this will be the net current flowing through this into 8, that is the resistance. So you can see from the next bit, that is from C, we have calculated the current I across this 8 ohm resistance, and we have got the voltage V output as 3.2 volts. So it has become very easy. Now I will like to discuss another point, like this was our previous question. In this case we had this as a voltage source plus 12 volt and we have a current source 3 ampere and 4 ohm. Now if you want to convert this part into a voltage source, then also it is very easy. You can convert this into voltage source. Then we have some resistances here, and this is a given voltage source. Now we are having two voltage sources and some equivalent resistance you have to calculate, and easily after that we can calculate the voltage across the 8 ohm resistance. So there can be several ways. Either you can start from the voltage or you can start from the current. Now using the source transformation method, you need to calculate what is the current in this circuit. So you can go through this types of examples, you can note it down, try to solve this. These are very easy, not so complicated, just you need to analyze them. I will give some hints. Here let us see, this is a current source with a parallel resistance, so it can be easily converted into voltage source. Same with the case of this case, that is a current source parallel to this 2 ohm resistance, so it will be having a voltage source of 4 volt each in these two cases. So after getting this 4 volt, we can calculate by applying KVL, and we will get the current I also. So it depends on you how you proceed, but the basic things or the technique is about transformation of the sources in a correct manner. Now next is the substitution theorem. Now what this substitution theorem tells, that suppose you have this type of circuit, this is a given circuit having 20 volt, 4 volt and some resistances. Now I can change this part, that is the last branch, into 8 volt. Can I? Yes, I can, because in this case I1, if you want to calculate everything or each of the elements in this case of this network, then in this case you will find I1 equals to 2 ampere, I2 equals to 1 ampere and I3 equals to 1 ampere, and V3, that is a voltage, is equals to 8 volt. Now I want to replace this third branch directly with the 8 volt voltage source. Now substitution theorem tells that you can replace any of these branches with whatever you want, any of this voltage source or current source, keeping all these values same. That is, the network will not change. The values in this network will never change. Now you can see I have converted this last part with a transform, or you can say better, I have substituted the last branch with a 8 volt voltage source, and still I1, I2, I3 and V3 remains the same. Now further I can also convert it as follows. I can convert it into a current source of 1 ampere, and still then also it remains the same. So this is the benefit of substitution theorem. According to your requirement or according to the ease which you need to progress, you can substitute the different types of sources, that is current source or voltage source, and you can make the problems regularly easier. So but the most important thing in case of substitution theorem is you need to analyze the circuits very well, so that other values do not get changed, and it needs a lot of practice. So you need to practice more in order to have a good hold on this type of theorems. Now if the voltage across and the current through any branch of a DC bilateral network are shown, this branch can be replaced by any combination of the elements which will maintain the same voltage across and the current through the chosen branch. So just before I have explained with some pictures or with some circuit diagrams about the substitution theorem, and this definition holds true for them. This is what I have already discussed. You can replace it with any voltage source and current source, keeping the circuit as same, or the elements of the circuit or the values, the regular values, to be same. Now coming to one of the most important theorem, that is the Thevenin's theorem. A linear two-terminal circuit can be replaced by equivalent circuit consisting of a voltage source VTh in series with a resistance RTh, that is a Thevenin resistance, where VTh is open circuited voltage at the terminals and RTh is the input or the equivalent resistance at the terminals when the independent sources are turned off. Now I think this statement has gone off your mind because this is too complicated to understand. We will discuss the problem so you will be very comfortable with this part. Now you see, this is the original circuit and this is the Thevenin equivalent circuit. Now for this calculating Thevenin equivalent circuit, you need to see the circuit from one side. You can go through the books, the processes of how to calculate these Thevenin circuits. you have to consider one side as open circuit, then you have to calculate the net resistance looking for the net resistance through that open circuit sided, and finally you can get RTH, VTH and so on. You can proceed. We will have a video basically on this Thevenin's and Norton's theorem afterwards. So as a basics of these theorems you just need to learn. So after seeing that example or some diagrams, now I will tell you how this works. A linear two terminal circuit you need to replace by equivalent circuit consisting of a voltage. Now a terminal circuit is given, that is a two terminal circuit. Now you have to replace with a net voltage and net resistance. That is the main aim of Thevenin. That net voltage is given as VTH and the net resistance is given as RTH, where VTH is the open circuit voltage. Now for calculating this VTH you need to have a open circuit voltage, and for that terminal at that terminal RTH is the input of the equivalent circuit, and that is also when the independent sources are turned off. So we'll go through some examples, so that will be very much easier for you. Now this is a network connected to the load. You can convert into a current source in this manner. Now this part will be is equals to this network with open circuit, potential across open circuit plus a current source. Now these Thevenin theorems have several cases, like consider two cases in finding RTH. First case is if the network has independent sources, just turn off all the independent sources, calculate the equivalent resistance of those resistors left. Means if the network has no dependent sources, that is they are not dependent on any other, or they are independent sources, just turn off all the independent sources, calculate the equivalent resistance of those resistors left. If the network has dependent source, that is some having dependent on current or voltage, there are two methods to get this RTH. And if the network has two dependent sources, there are two methods to get this RTH. The first method is turn off all the independent sources, apply a voltage source V0 or current source I0 at terminals A and B, and determine the resulting current I0, and this will be the resulting voltage. Then RTH will be V0 by I0. Now suppose this is a circuit, and this circuit is having all independent sources, and these independent sources are set equal to 0. Now after that you can calculate easily this RTH, that is equals to V by I. Suppose the circuit with all independent sources set to 0, and if it has a current source, then also you can easily calculate RTH will be V0 by I0. We will go through some of these numericals, then it will be quite easier after solving problems. Now case 2 is if the network has dependent sources, there are two methods to get this RTH. Calculate the open circuit voltage and the short circuit current at the terminal. Now for the network having dependent sources, just take out the voltage, that is open circuit voltage you need to calculate for the same original circuit, and for the same original circuit you need to calculate the short circuit current, and after getting both the values you can get RTH as open circuit voltage divided by short circuit current. So this was all about our video. In the next we will see some more theorems and about the Thevenin's and Norton theorem also. Thank you.